Today we are going to start determining limits algebraically. Our objective is to use algebraic techniques to find limits. So far, we've determined limits graphically, numerically, using the limit properties, and then using tables. The drawbacks behind the tables are that it's tedious, and you can't always see what's going on, or can't always clearly see. We've also used substitution. The problem is that occasionally we're going to have situations where we get 0 over 0. And that is, bad because we're dividing by 0. So the way around it is that we're going to use algebra. All right, so that 0 over 0 is called an indeterminate form. And we're going to use the following techniques: factoring, long division, multiplying by a conjugate, trig identities, or finding a common denominator to work our way around it so that we can determine the limit. So if we look at the first example, we'll substitute the 3 first to see if we do have an indeterminate form. And we have 3 squared minus 9, which is 9 minus 9 or 0, and that is clearly over 0. So we'll go ahead and factor. We're going to use our correct notation. So the limit as x approaches 3, x plus 3 times x minus 3 over x minus 3. We can see that the x minus 3's cancel out. And so we're left with the limit as x approaches 3 of x plus 3. When we substitute, we can see that we're no longer in an area where we have an indeterminate form, and so our limit is equal to 6. So in this case, we factored. In the second example, again, we're going to substitute first. If we plug in a -4, we do end up with an indeterminate form because we have 0 in the numerator and 0 in the denominator. So again, we'll factor. We're going to use our correct notation. So the limit as x approaches -4, 2 times the quantity x plus 4, and the denominator factors to x plus 4 times x minus 3. Again, we'll cross out that common binomial factor, and we're left with a limit as x approaches -4 of 2 over x minus 3. Clearly, we no longer have an indeterminate form because we have a 2 in the numerator. So we can go ahead and substitute, and our limit is approaching -2/7. In the third example, we'll check our substitution. If we plug in 0, we end up with the square root of 16 minus 4, which is 0 over 0, so we have an indeterminate form. In this case, because we have a square root, we're going to multiply by the conjugate, even though it's in the numerator. And the conjugate of this is the square root of x plus 16 plus 4. And this leaves us with a difference of squares in the numerator. So again, paying close attention to our notation, the limit as x approaches 0. The numerator becomes a squared minus b squared. So we'll have x plus 16 minus 16. In our denominator, we're going to leave it in factored form. Never, ever, ever try and multiply these together. It makes it very convoluted, and you won't be able to really see your way out of it. So we'll just leave it as the two factors. Then we'll take the limit as x approaches 0. The numerator simplifies to x. The denominator has x times that conjugate. And we can see that we have a common monomial factor of x, so we can cross them out. Again, making sure we keep our notation. It's the limit as x approaches 0 of 1 over the square root of x plus 16 plus 4. Now, when we substitute 0, we no longer have an indeterminate form, and so our limit as x approaches 0 of this function is going to equal 1/8. In example 4, we clearly have trig, so we will stick with a trig identity. If you're not sure what the sine of 2 theta is, the identity is that the sine of 2 theta equals 2 sine theta cosine theta. And as you can see from the blue bubble, every time you see a trig identity, you're responsible for knowing it for in the future. So keep a running list somewhere in your notebook to keep track. So now we'll go back to our limit. We'll have the limit as theta approaches pi of 2 sine theta cosine theta over sine theta. We can see that the sine thetas cancel out, and we're left with a limit as theta approaches pi of 2 cosine theta. Clearly no longer an indeterminate form because we no longer have a denominator. So we can substitute in the pi. The cosine of pi is -1. 2 times -1 means that our limit is 2. All right, let's take a look at example number 4. We have several fractions. When we plug in 0 for delta x, we have 2 over x minus 2 over x, so we have a 0 in the numerator and a 0 in the denominator. So we're going to try and clear out our fractions to clear out this indeterminate form. We're going to treat delta x as if it's a single variable, like a y. So that would mean that our common denominator is x times x plus delta x. We'll multiply the numerator and the denominator of our complex fraction. So we'll have the limit as delta x approaches 0. For the first fraction, when we're multiplying, the x plus delta x cancels out with this factor of x plus delta x, and we're left with 2x minus the 2. This time the x is crossed out, and we have the quantity x plus delta x. So we've cleared out those fractions. And then in the denominator, we have delta x, x, and x plus delta x. And again, don't try and FOIL your denominator together. You want to leave it in factored form. Now we'll go ahead and clean up our numerator. So it's the limit as delta x approaches 0, 2x minus 2x minus 2 delta x over delta x times x plus delta x. We can see that the 2x's cross out, and we're left with a limit as delta x approaches 0 of -2 delta x in the numerator. And then we have delta x, x plus delta x in the denominator. And delta x is just a variable like y, so we can cross out that common factor. And then we're left with a limit as delta x approaches 0 of -2 over x times x plus delta x. We no longer have an indeterminate form because there's no longer a 0 in the numerator, so we can go ahead and substitute. We'll get -2 in the numerator, and then x times x plus 0 is x squared. So our final answer is negative 2 over x squared. Okay, last example. We're back in the land of polynomials. So we check real quickly. We plug in a 2 in the numerator, we get 0. We plug in a 2 in the denominator, we get 0. So having substituted into an indeterminate form, we'll go ahead and start factoring. Since this polynomial does not readily appear to factor by grouping, I'll go ahead and try synthetic division. Try 2 first, just with the idea that hopefully the x minus 2 would cancel out. So we'll do some synthetic division over here on the side. So we'll put our root 2 in here, or our root of 2, and then the coefficients 3, negative 5, negative 3, 2. Bring down the 3. 3 times 2 is 6. Negative 5 plus 6 is 1. 2 times 1 is 2. Negative 3 plus 2 is negative 1. And 2 times negative 1 is negative 2. So happily, this did factor using the synthetic division. So we can go back again, make sure you write the limit as x approaches 2, or the limit as x approaches whatever, every single time until your final substitution. So having factored using synthetic division, we'll have x minus 2 times the quantity 3x squared plus x minus 1, which does not factor any further. And then in x minus 2, we can see that the binomial factor cancels out. And so then we have the limit as x approaches 2 of 3x squared plus x minus 1. Clearly no longer in indeterminate form, so we can go ahead and substitute the 2, and our final answer becomes 13. All right, let me know if you have any questions.